Welcome back to another video in the Descriptive Statistics series. In this section, we will discuss tabular and graphical summaries, why they are essential components of descriptive statistic, and how they can provide clear and concise ways to present and interpret data. These methods help researchers and analysts understand the main features of a dataset, making it easier to identify patterns, trends, and insights. Consider this simple example. We want to visualize purchases made from a vending machine that sells various products, such as Coke Classic, Diet Coke, Pepsi, Dr. Pepper, and Sprite. We are given a sample dataset comprising 50 soft drink purchases, as displayed in Table 1. We can use both tabular and graphical summaries to effectively present the data and gain insights into consumer preference. If we want to study 50 purchases made from the vending machine, simply listing all individual purchases in a table is not the most effective way to display the information. A more informative approach would be to summarize the data by listing each sold product along with a count/frequency of how many of each item was sold. This method allows us to quickly identify which products are the most popular and gain insights into consumer preferences. Generally, to summarize categorical data through frequency counts, relative frequencies, and percent frequencies, these are steps we need to take. Here's a breakdown of each concept. The first step in analyzing categorical data is to identify and list all possible values or labels that can occur in the dataset. This involves recognizing each unique category represented in the data. If the data is ordinal, the values should be arranged in an appropriate order based on their ranking. For instance, if the data consists of satisfaction ratings, for example, excellent, good, fair, poor, these should be listed in the order of their ranking. Next, we calculate the frequency of each value. Frequency refers to the count of how many times each specific value appears in the dataset. This step helps summarize the data by showing how often each category was observed. For example, if we have a dataset of 50 purchases from a vending machine, we might find that Coke Classic was purchased 19 times, Diet Coke 8 times, and Sprite 5 times. To understand the significance of each frequency, we can calculate relative frequency. This is done by dividing the frequency of each observation by the total number of observations. The relative frequency gives us the fraction of times each value was observed in relation to the entire dataset. For instance, if Diet Coke was purchased 8 times out of 50 total purchases, its relative frequency would be 8 divided by 50 is equal to 0.16. This relative frequency can also be interpreted as the probability of observing that value if we continue sampling, meaning that there's a 0.16 chance of purchasing Diet Coke based on this sample. Importantly, the sum of all relative frequencies in the dataset will equal 1. Finally, we can convert relative frequencies into percent frequencies by multiplying each relative frequency by 100. This provides an easily interpretable percentage that indicates the share of each value within the dataset. Continuing with our example, if the relative frequency for Diet Coke is 0.16, its percent frequency would be 0.16 times 100 is equal to 16%. The total of all percent frequencies will sum to 100%, allowing for a straightforward representation of the distribution of categories within the dataset. By moving from listing all purchases to reporting frequency, relative frequency, or percent frequency, we present the same dataset in a much more efficient way. This approach enhances clarity, highlights patterns, facilitates comparison, and improves communication, ultimately allowing for better decision-making based on the analyzed data. A bar graph, or bar chart, is a visual representation of data that uses rectangular bars to display the frequency, count, or other measures of different categories. Each bar's length or height is proportional to the value it represents, allowing for easy comparison between categories. The categories are typically displayed along the horizontal axis, x-axis, while the values are indicated on the vertical axis, y-axis. Bar graphs can be oriented vertically or horizontally, with spaces between the bars to emphasize that the categories are distinct. They often incorporate different colors for each bar and may include labels for clarity. Bar graphs are widely used in various fields to present categorical data, making it easier for viewers to understand trends, comparisons, and insights at a glance. By using a graph, we can significantly enhance the representation of the data. A bar graph in particular, offers several advantages over a frequency table. Bar graphs are more engaging and easier to interpret than numerical data presented in tables. They facilitate quick visual comparisons between categories, allowing viewers to easily identify which items are more popular at a glance. The graphical format clarifies relationships and differences in the data, which aids in understanding. Bar graphs are more accessible to a wider audience, transcending language barriers and numerical literacy. They can incorporate features like colors, annotations, and data labels, providing additional context for the information presented. We can further enhance this bar graph by ranking the items according to the quantity sold. A pie chart is a circular statistical graphic that is divided into slices to illustrate numerical proportions. Each slice represents a category's contribution to the whole, with the size of each slice corresponding to the percentage of that category in relation to the total. Pie charts are particularly effective for displaying relative proportions, making it easy for viewers to see how individual categories compare to the overall dataset. Advantages of pie charts over percent tables. Pie charts provide a clear visual representation of data, allowing viewers to quickly grasp the distribution of categories. The circular format makes it intuitive to see which categories dominate and how they relate to the whole. The size of each slice makes it easier to compare proportions at a glance than reading through numerical percentages in a table. Viewers can easily identify which categories are larger or smaller. Pie charts condense complex data into a single graphic, which can be more engaging and easier to understand than a table full of numbers. Pie charts effectively highlight the composition of a dataset, showing how different parts contribute to the total. This can be particularly useful in presentations or reports where understanding the overall picture is crucial. For audiences with varying levels of numerical literacy, pie charts can provide a more accessible way to interpret data. The visual nature of a pie chart transcends language and mathematical understanding. You can find a full tutorial on how to develop the charts provided in this slides in the provided link. When dealing with quantitative data, especially datasets with a wide range of values, listing all possible values becomes impractical. Even if it were feasible to create a frequency table, such a table might not provide a meaningful summary of the data. For instance, if you have a dataset containing hundreds of values like test scores or measurements, simply presenting each score in a table wouldn't effectively convey the distribution or the central tendencies of the data. The simplest way to address this problem is using a stem and leaf diagram. A stem and leaf diagram offers an informative way to visualize quantitative data while retaining the actual data values. This method allows for a clear display of the dataset while facilitating the identification of patterns, shapes, and distribution characteristics. Construction steps for a stem and leaf diagram are: divide each number. Each data point xi is divided into two parts: a stem, which consists of the leading digits, and a leaf, which consists of the last digit. For example, in the number 47, 4 is the stem and 7 is the leaf. List stems vertically. The stem values are organized in a vertical column. Each unique stem appears once, which helps group similar values together. Record leaves beside stems. Next to each stem, the corresponding leaves for each observation are recorded. This allows for a side-by-side visual representation, making it easy to see how data points cluster around certain values. Units. It's essential to label the units for the stems and leaves on the diagram to provide context for the data being represented. Stem and leaf diagrams have advantages. Unlike other summary statistics that aggregate data, stem and leaf diagrams maintain the actual data values, allowing for a detailed understanding of the dataset. They provide a clear visual representation that can help identify the distribution, center, and spread of the data, making it easier to analyze, and stem and leaf diagrams are relatively simple to create and interpret, making them accessible for various audiences. Table 2, on the left, reports the number of products sold over 80 days. To visualize this dataset, we can use a stem and leaf diagram on the right. From the stem and leaf diagram, we can observe that the smallest number of items sold in a day is 24, while the largest is 76. Additionally, it is common to see sales figures ranging between 130 to 170 counts. Histograms can serve as an extension of stem and leaf diagrams to visualize quantitative data. A histogram is a graphical representation of the distribution of numerical data, illustrating how data points are distributed across specified intervals or bins. Each bar in the histogram represents a range of values, with the height of the bar indicating the frequency of data points that fall within that range. Histograms are typically used for continuous data, where values can fall anywhere within a range. Unlike bar graphs, histograms do not have gaps between the bars, emphasizing the continuous nature of the data. The horizontal axis, x-axis, represents the bins or intervals, while the vertical axis, y-axis, shows the frequency of data points. Histograms are valuable tools in statistics and data analysis, as they help identify patterns, trends, and outliers, making it easier to interpret and analyze numerical data effectively. The steps for constructing a histogram include: determine the optimal number of bins. Label the bin class interval boundaries on a horizontal scale. Mark and label the vertical scale with frequencies, relative frequencies, or percent frequencies. Above each bin, draw a rectangle where the height is equal to the frequency or relative frequency corresponding to that bin. To create a histogram, we first need to determine the appropriate number of bins for our dataset. We can use Sturge's formula to determine the number of bins, which is calculated as 1 plus the logarithm of the size of the dataset, n, in base 2, rounded up. For example, with a dataset of size 80, we calculate the logarithm of 80 in base 2 plus 1, which equals 7.32. When rounded up, this gives us 8 bins. Next, we need to find the length of each bin by dividing the range of the data, maximum value minus minimum value, by the number of bins, 8 in this case. This calculation yields a bin length of 21. Once we determine the number and length of each bin, we place them on the horizontal axis and count how many data points fall within each bin. These frequencies are then represented as rectangles above each bin. Histograms can indeed be misleading, primarily due to the choice of bin size and the number of bins used to represent the data. The use of specific formulas for determining the appropriate number of bins is essential to prevent misuse and manipulation of histograms. For example, consider these 4 different histograms displaying the same dataset, but with varying numbers of bins assigned to each. This simple change in bin count can dramatically alter the appearance and interpretation of the data. One histogram shows a smooth distribution, while another displays the illusion of a skewed dataset, leading to different conclusions about the underlying data. This illustrates that the choice of bin width and the number of bins can significantly influence how the data is perceived. Consequently, even when histograms are created from the same dataset, they can represent different aspects of the data or suggest different populations based solely on their bin configurations. Therefore, it's crucial to carefully consider how histograms are constructed to ensure they accurately represent the data and do not mislead the viewer. A left-skewed distribution, also known as negatively skewed, is characterized by a longer or fatter tail on the left side of the distribution. In this shape, the peak of the histogram is typically located on the right side, indicating that most data points are concentrated toward the higher end of the scale. As a result, the left tail extends further than the right. In terms of central tendency, the mean is usually less than the median. This occurs because lower outliers pull the average down, even though the majority of the values are relatively high. Left-skewed distributions are commonly found in scenarios where there is a natural lower limit, such as the age at retirement, where most individuals retire around a certain age, but a few may retire significantly earlier. A symmetric distribution is defined by its balanced shape, where the left and right sides of the distribution mirror each other. In this case, the tails on both ends are approximately equal in length, and the peak of the histogram is centered in the middle. This symmetry indicates that the data is evenly distributed around the central value. In symmetric distributions, the mean, median, and mode are all located at the center, making it easier to interpret the data. The classic example of a symmetric distribution is the normal distribution, often represented as a bell curve. Such distributions are commonly observed in natural phenomena, where various factors tend to cluster around a central tendency. Right-skewed distributions, or positively skewed distributions, are characterized by a longer or fatter tail on the right side. In this shape, The peak of the histogram is generally found on the left side, indicating that most data points are concentrated toward the lower end of the scale. The right tail extends further than the left, resulting in a mean that is typically greater than the median. This skewness suggests that while the majority of values are relatively low, a small number of high outliers pull the average upward. Right-skewed distributions are commonly encountered in situations such as income distribution, where a small percentage of individuals earn significantly more than the majority, leading to a concentration of lower incomes and a few high earners. Understanding these characteristics is essential for interpreting data accurately and applying appropriate statistical methods. Two-peaked histograms feature two distinct peaks that indicate the presence of two prevalent characteristics within a dataset. A common example of this can be observed in traffic patterns throughout the day. For instance, if we analyze the number of cars passing through a particular intersection, we may find that there are two significant peaks, one during the morning rush hour as commuters head to work and another in the evening when they return home. Each peak represents a mode, reflecting the times of day when traffic volume is highest. This bimodal distribution suggests that traffic patterns are influenced by two different groups of drivers, morning commuters and evening travelers, each with their distinct driving behaviors and schedules. Understanding this two-peaked distribution can help urban planners and traffic engineers implement effective traffic management strategies to address congestion during these peak hours. Truncated histograms occur when the data displayed is cut off at a certain point, either intentionally or unintentionally, resulting in a misleading representation of the overall distribution. This can happen if the histogram only includes data within a specific range, omitting values that lie outside this range, which can significantly distort the interpretation of the dataset. Data might have been manipulated at the point of entry for various reasons, such as to emphasize a particular trend, achieve a desired outcome, or mask negative results. For example, if a company is reporting sales figures, they might truncate the histogram to exclude data from a period of poor performance, making it appear as though sales are consistently rising. This manipulation can lead to incorrect conclusions and decisions based on incomplete information, highlighting the importance of transparency and accuracy in data collection and representation. Incomplete histograms arise when critical information is missing or misrepresented in the graphical display, leading to a distorted understanding of the data distribution. This issue can occur if the data is rounded improperly, which may cause data points to be inaccurately grouped into bins, thus obscuring important patterns or trends. For example, if the heights of individuals are rounded to the nearest foot, subtle variations within a range can be lost, resulting in fewer bins and a misleading representation of the actual distribution. Additionally, using too many bins can lead to an incomplete histogram, as the data may be spread too thinly across many intervals, making it difficult to discern the underlying trends or patterns. Consequently, this excessive binning can create a fragmented view of the data, potentially hiding significant peaks or trends that would be more visible with a more appropriate binning strategy. Cumulative frequency is a statistical concept that represents the total number of observations that fall below a particular value in a dataset. It is a running total of frequencies, providing insight into the distribution of data by indicating how many data points lie at or below each specific value. Cumulative frequency is particularly useful for understanding the overall distribution of quantitative data, allowing analysts to determine the proportion of observations that fall within certain intervals. For example, in a cumulative frequency table, one might track the number of students scoring below various grade thresholds, such as the number of students scoring below 50, 60, 70, and so forth. By accumulating these frequencies, one can easily assess how many students performed below a certain score, making it a valuable tool for analyzing data trends and making informed decisions based on cumulative results. Cumulative frequency can also be visually represented through cumulative frequency graphs, which help to highlight trends and patterns in the data. Cumulative frequency is a statistical concept that represents the total number of observations that fall below a particular value in a dataset. It is a running total of frequencies, providing insight into the distribution of data by indicating how many data points lie at or below each specific value. Cumulative frequency is particularly useful for understanding the overall distribution of quantitative data, allowing analysts to determine the proportion of observations that fall within certain intervals. For example, in a cumulative frequency table, one might track the number of students scoring below various grade thresholds, such as the number of students scoring below 50, 60, 70, and so forth. By accumulating these frequencies, one can easily assess how many students performed below a certain score, making it a valuable tool for analyzing data trends and making informed decisions based on cumulative results. Cumulative frequency can also be visually represented through cumulative frequency graphs, which help to highlight trends and patterns in the data. You can enhance scatter plots by incorporating additional information, such as displaying histograms of your variables of interest, petal length, and petal width in this case, or adding a trend line to emphasize the relationship between the two variables. In the case of the iris dataset, the scatter plot often reveals distinct clusters, indicating that different iris species can be separated based on their petal characteristics. Additionally, scatter plots can help detect outliers, points that fall far outside the general pattern, which may warrant further investigation. Pair plots are created to visualize the relationships between multiple pairs of variables within a dataset, allowing analysts to explore potential correlations and patterns across all combinations of those variables simultaneously. Each pair plot consists of a grid of scatter plots, with each plot representing a unique pair of variables, making it easy to identify relationships, trends, and potential outliers across the entire dataset. The relationship between pair plots and scatter plots is that scatter plots serve as the foundational building blocks for pair plots. While scatter plots illustrate the relationship between two variables, pair plots expand this concept to multiple variables, providing a comprehensive overview of the interrelationships within the data. This multidimensional visualization is particularly useful in exploratory data analysis, enabling researchers to quickly assess how different variables interact and helping to inform further statistical analysis or modeling. Python boasts a wide range of libraries designed to enhance data visualization and dashboard creation, allowing users to present complex information in more accessible and engaging ways. Prominent libraries such as Plotly and Bokeh enable the creation of interactive plots and dashboards that facilitate a deeper understanding of the data by allowing users to explore various aspects dynamically. For example, users can zoom in on specific data points, hover for detailed information, or filter data in real time, all of which contribute to a more intuitive representation of the data. You can find code scripts on our Canvas page to learn how to work with popular visualization libraries such as Matplotlib, Seaborn, Bokeh, and Plotly. Thank you for watching this video.